This presentation is on impact of chemical mixtures on time-dependent workability and rheological property of UHPC. Most of the work is done by my PhD student Flavia, which I believe she's in the audience. On the official website, actually have a different title, which is on static and dynamic flow of UHPC with different mixed proportions. So when we're looking into these, because this section is on unlocking workability issues, I feel this is more appropriate. We do have some mention about the different tests on flow, but our focus is actually covering different kind of thing. So the research is actually sponsored by Nebraska Department of Transportation. We had a project finished in 2018. We have another project coming, which will be looking more into this. So a lot of ongoing work. Outline of this presentation, we'll be talking about, give you some background about some challenge of UHPC during production and handling. And another thing is how to evaluate workability and fiber stability. And then we're going to show you something related to the quality control index that we propose for UHPC workability. And then we'll have some test methods and results showing after. I'll have a couple of slides showing you some field production and placement of UHPC. Then we'll wrap up with conclusions and final remarks. So this is basically just like the ugly. If you have the good, the bad, the ugly. So I show you some potential issues. So for those who work with UHPC, you know that it is a very amazing material, but on the other hand, it's kind of hard to control. So over here, what you see are some examples we see in the lab in the field. The first one is a lack of workability. So if you look into this is one of the precast section we plan to cast. Apparently, you can see how tough it is to mix that, to move that. And then if you cast a cylinder, you're going to get a very uniform shape of cylinder like this. On the other hand, you might have a very soupy mix. It's not a very technical term, but you know what I mean. You have fiber segregation like this. And basically, you can even see that in fresh concrete. And if you cast cylinder, you might end up with segregation like this. The other thing that I'm not going to mention, but we often see during the preparation, is the fiber boring issue. So this is an issue usually associated with when you load the fiber into the mixer too fast or it come into a trunk, it stays in the trunk. So this is what we see, a nicely picture of a fiber bore over here. The other thing is elephant skin. I don't know how many of you see this before. Let me see if I can play the video. So close, I'll turn the volume down so that I can talk. So this elephant skin is something you commonly see that if you let the concrete UHPC, meaning UHPC way there, you don't need to see this part. So if you let the UHPC sit there for a few minutes or even longer, you're going to see this elephant skin. What happened is because the unique short speed behavior of the UHPC, you see this happen. I mean, it is not going to be an issue if you are able to place a concrete right away. But particularly if you're dealing with a large sample or element, if, for example, if you have to have multiple batch, it could be an issue. But based on this, one of the things you might need to look out for is if you let a concrete sit there for a long period of time, you might have some issue. So what's in our toolbox? So there are a few different kinds of tests people have been using to measure the workability of UHPC. These are the common used one. Early on, we have another section of UHPC workability, and some people present different kind of masses. So traditional flow table test based on ASTM 1437, and then the new 1856 is actually have a section cover the workability of UHPC that's also based on the flow table. So the difference is if you use the dropping or not, or free flow. So the criteria flow range people usually use is between 8 to 10 inches. So that's again what people commonly been using. Move on a few other things. So from a fresh concrete standpoint, when you look at the flow or workability of UHPC, even those usually when we report, we only report the flow in inches. As you see in previous slide, 7 to 10 inches, 8 to 10 inches, usually pretty good indication of the workability of UHPC. But on the other hand, there are more information we can get. For example, if you see this over here, you saw this earlier about the fiber segregation. So fiber segregation is, if it's severe, it's clearly visible during the construction. During the fresh concrete stage. On the other hand, the other thing you can use is compare the static flow, meaning you just remove the flow cone and match the flow versus dynamic. That means you have to vibrate. So, and you can see the difference over here, especially if you let it sit there for a few minutes, you can clearly see difference. So the other thing is the rheology. So forgive me, I have someone get urgency in the house. Just if it's okay with you, I'm gonna.
No worries.
Stop.
We can just take a short break. No worries.
Yeah. How about this? If we can have the next speaker to talk first, and then I'll come back. Very sorry about this.
No worries.
Yep. So, yeah, that's what we can use in the fresh concrete state. We have another tool of rheology. But on the other hand, if you get into hardened concrete, so again, usually we measure strength in different kind of mechanic property, but I want to show you there are a few things you might want to look into, which is directly related to workability and fiber stability. One thing, of course, is consolidation. If you see a bad cylinder or during construction, you see the issue, that's a good indication. And this picture over here in the middle show you the fiber consolidation, fiber segregation. The other thing is over here, and if you do the compressive strength of UHPC test, you know that you have to grind two ends so that you can actually clearly see if you have indication of segregation or not. With this, at the bottom end, you have fiber. You probably cannot see very well, but the top part clearly with no fiber. That's another sign. And even on the broken cylinder, you can see if the break is uniform or not. So what I want to show you the last two slides, there are a lot of information you can get with some traditional tests. You just need to pay more attention on this. So some ideas to borrow. I mean, we have been using flow table to match the workability of UHPC for quite a while. This has been the only test, even though it's from researchers' standpoint, we do rheology and different kind of tests. But on the other hand, can we do something better than this? Because the issues you see over there relate to segregation, fiber stability. So the idea we kind of borrow is from SCC. Many of you probably familiar with SCC. First thing is VSI, visibility stability index. You can see whether you have rain or not, that indication of the stability of the mix. The other thing is the segregation with fiber. So with that, the thing we kind of propose is a very similar index compared to SCC. So with the VSI index of UHPC with highly stable, with no visible fiber separation, and then you have slightly separation, and then you can see the fiber over here. That's an index of 2, then 3, and very severe one, that's 4. Usually by the time you see this, you can see this is pretty bad. On the other hand, similar to the HVSI and SCC, that's the index we propose. Again, it is pretty much empirical. I do think that there are more work to do, but hopefully this gives us some idea, something we might be able to do. So with highly stable versus, you can start to see segregation. Again, we provide different recommended index. So the other thing is consolidation index. This might not be as critical, as important, because you see this already. So, but for the VSI, HVSI, these are the two index. Hopefully we can like use these for, incorporate these into ASTM or Astro standards with more data and more inputs from the industry. So getting into the main program. So as I say, that the work we've done over here is actually focused on workability change over time with different chemical admixtures. So what we did is that right after mixing, we do the different workability and rheology tests, and then let it sit there for 15 minutes. Every 15 minutes, we run the test again. Before we run the test, we hand mix a little bit just so we can remove that structural buildup. And the test we did is a flow table test as well as the rheology test. So the flow table test, we use a standard 10-inch flow table. What you see graph over here is because a lot of people have been using the standard flow table, but what if you have a flow more than this? So that means you flow it out of the table. Standard say two minutes. What if you flow out of the table before that? So we actually have a equation we developed that can predict the flow in case you have the standard 10-inch flow table. Meaning if you float out of the flow table in 23 seconds, we can kind of project the flow, which will be higher than 10-inch apparently. The other thing we do is rheology test. So we basically have a standard up curve and down curve, and then we measure the shear stress and shear rate, use that information to calculate the yield stress and viscosity. So the mix design are pretty much all the same. We use a base mix we developed with our Nebraska DOT project. The only thing we change basically is the chemical mixture dosage. What you see over here is that one set is high range water reducer, the other set is with workability retaining admixtures, another one is anti-foaming admixtures. So the reason, well, everyone know high range water reducer is something we definitely need. On the other hand, there are a lot of experience or issues with the workability, how long it's going to last. So that's why we introduced this workability retaining mixture. The other one is anti-foaming admixtures, because as some of you might notice, when we mix UHPC, because the mix is kind of viscous, you tend to have a lot of air bubble trap inside. That could reduce the workability. So we actually use that. There are some reports actually successfully demonstrate that this will help. So we actually include this as well. So let me show you some results. So this graph, just so you know, is time versus flow. You can clearly see that with the time elapsed, the flow dropped dramatically. And on the other hand, there are two numbers over here. The first number is VSI, the other number is HVSI. So if you see number 0, that means it's good. But if you see something high over here, like 3 and 3, 1 and 4, that means it's just a not stable mix. So it's as expected. You can see that with the elapse of the time, you can see the workability of flow drop dramatically, and depend on the dosage of chemical mixture. Like in this case, high range water reducer, you can see we might start with a highly unstable mix and get into a fairly stable mix. So two takes from this one is, one, you do expect a dramatic drop with workability over time. The other thing is that if you do end up with a highly unstable mix in the field, don't panic. I'm not saying you're safe. On the other hand, that if you keep mixing for a little bit, give some time, you might be able to get back to a normal mix. So that's one of the things we observe. The other thing is workability retainer mixture. As you can see that with the workability retainer mixture, over time, you can see that it can extend the time for you to work with concrete to over 2 hours. So which is very important, especially if you're dealing with a large construction. So the other thing is kind of coming to surprise is anti-foaming the mixtures. You can see with that introduction of anti-foaming the mixture, the job of the flow is very fast. So likely that's because you remove all the air bubbles, somehow kill your workability as well. So that's something that it's possible to use, but you need to use with caution. So relate to the flow and stability based on the proposed consolidation index. So a minimum of 170, that's about 170 millimeter, which is about 7 inch of flow is needed for UHPC mix to achieve self-consolidation. And that you can see that some example of not that well mixed, that lack of consolidation. So when we look into the flow time, and stability, so the thing we observe is that if you do have flow, a mixed flow out of the table, meaning you have a more than 10 inch of flow, it is okay. But on the other hand, when the flow time is too fast, meaning if you flow out of the table very fast, very likely you can end up with some non-stable mix. So kind of based on our data, we say about if you float out the flow table within 45 minutes, you have a pretty good chance of fiber segregation in the hardened state. So relate to rheology, one of the things we observed that both Bingham model and modified Bingham model can be used to predict. Both of them have pretty good R-square, but the modified Bingham model is probably a better model to use because it's not actually a straight line. You can see over here. So, and this is a BC table. I don't expect you to see and read everything, but basically you can see that with the time elapse, you can clearly see the viscosity increase geometrically. And then you reach a certain point like overload, meaning that you just cannot use this for the test. So moving on about the viscosity versus flow, as you can see over here, that is, there are a few things you can see over here. Viscosity will decrease with the flow, and this is kind of expected. And then related to yield stress is not as clear. And then if you do have a highly flowable mix, so this is flow time. If you're talking about flow time, meaning flow out of flow table, then we don't have a clear relationship you can see over there. So relate to the stability index versus viscosity. So based on the data, what we see over here, if the viscosity is lower than 100 pascal per second, you'll be seeing some issue about stability. So that's basically our results. So the next couple of slides show you some field or plant production of UHPC. What you see over here, a couple of things we have been using and we get some good experience. One of them is UHPC is a material require a lot of mixing, and with all the fine content, the temperature of the UHPC drop a lot. From the workability standpoint, this could potentially be an issue when the temperature is getting too hot. So apparently you don't want to get the temperature higher than 90 degrees Fahrenheit. The other thing is fiber. So it is very difficult to load fiber. Is basically with the plant we visit, this usually is the most time consuming part. And you can certainly use a fiber dispenser if that's available. If not, these will probably work. Have a screen and then feed the fiber in during the mixing. Of course, this will still take some time. You just need to make sure that you have enough manpower to do that. On the other hand, a few examples of what you see in the field. This is a mix with a very high viscosity, apparently. This is mix you can barely work with, but actually with the same mix after a few minutes, this is what you see over here. We can barely work with that concrete. So that's something just to show you within a few minutes, you can see that trend dramatically. On the other hand, another mix over here, that's a mix we recently did in South Dakota. You can see a very good mix over here with some slight fiber segregation, not very severe, but you can see the consistency of the mix. Very viscous, but flow very, very well. So with that, I just want to wrap it up. In the interest time, I'll just be brief. So definitely the role of chemical mixture is very important. You'll be observing a reduction in workability in UHPC over time, but workability retainer mixture will be very important, very good tool for you to use if you want to extend that life of the concrete. And then anti-foaming of the mixtures could dramatically reduce workability. If you want to use it, use with cautious. The index we propose, VSI, HVSI, as I mentioned, that even though it's not very mature, but hopefully more and more people can look into this and we can work it with ASTM, Astro, develop something that people can use in the field to better control the workability of UHPC. And then the other thing is the viscosity and sextropy of the UHPC. With the time elapsed, you can see a dramatic increase, which oftentimes result in an issue with the concrete placing. So for the sextropy issues, if it's possible, keep agitating the UHPC. The other thing is use workability retainer mixture to buy you some more time. So the other thing related to viscosity is, based on our result, we recommend at least 100 Pascal per second to have a more stable mix. With that, I'm going to conclude this presentation. So this is a picture that from the South Dakota plant we visit. So with that, I would like to entertain a couple questions. So, okay, I have a question on how do I evaluate sextropy. So from a rheology, what we do, I'm assuming this question is related with rheology, from the rheology test. So if you look into the graph over here, basically the area in between, we use this to define the sextropy. Hopefully that answers the question. Okay, looks like another one. How does the ambient temperature affect your science? It's not necessarily affect my science, but it is very important. I won't say that it's necessarily the ambient temperature, the mixed temperature is probably more important. Clearly, you need to be very cautious if the temperature is high. As I say that if you're dealing with environmental temperature fairly high, use ice. You use as much as 50% or even higher amount of ice to make sure we reduce that. Ideally, you want to make sure by the time you finish mixing, you have temperature of the mix no higher than 90 degrees Fahrenheit. That's what we're shooting for. Those videos are done in a precast setup. And so, and the other one is thank you. So thank you for the time.